So good morning again, and I would like to wish you all a good day and welcome to the fourth edition of the series of workshops on quantum low-dimensional magnetism. This series was, at the beginning, it started in 2017 as an initiative of a group of colleagues that were collaborating under the support of the Federal Brazilian Agency, CAPES, that involved the Federal University of Alagoas, Federal University of Lavras, and the Shastry University from Slovakia. And by the end of the project, we thought in organizing this series of events to keep the collaboration going on and also to join new members for this group that were interested in working with quantum low-dimensional magnetism. So the first edition, it took place here in Maceió, and the second edition was organized by the colleagues from the Federal University of Lavras. The third edition was fully online because of the COVID pandemic. It was a very nice online meeting that took place last year. And now we are organizing this fourth edition in this hybrid form. Some colleagues are here present in Maceió, and some of you are participating by this Google Meet room. And I would like to thank you all for the efforts of participating of this meeting, the colleagues that are here in Maceió, and also the colleagues that are taking your time to contribute to this meeting online. I would like to express our gratitude to the local research foundation from the Alagoas State. It's named the FAPEAL. This foundation it gave us some financial support to make it possible to bring some of you here to Maceió. I would like to express my full gratitude to this agency. The conference will be in a hybrid format, as I told you before. Some of the presentations will be online in this meeting room that you all have the link, and some of them will be delivered on site, but we are going to transmit also this on-site talks through this meeting room. And I hope that we have a very pleasant and productive week during this workshop. And for you that are visiting Maceió again, I wish that you may arrange some time to visit the city and see the attractions that we have here. And for you all that are online, I wish that you can come in a future opportunity to know and to see the charming city of Maceió. I would like to thank also the direction of the Physics Institute of Maceió for allowing us to organize this meeting here at the auditorium, and also to the graduation program in physics of Federal University of Alagoas, that they are hosting our visitors. So the program today will have 4 talks, and 3 of them, the first 3 of them will be delivered online, and the last one will be delivered here at the auditorium of the Physics Institute. The first talk will be delivered by Professor Andreas Honecker from Paris University, and I would like to thank him for taking this time to contribute to this series of events. And I hope that you can, in a future opportunity, come to Maceió and visit our group and know this very enchanting city. So thank you very much, Professor. And I think you are already sharing your screen.
Yes. Please.
Okay, thank you very much. Can you hear me?
Sure, we can hear you well.
Okay, let's go.
That's all, you can start.
Okay, so first of all, I would like to thank the organizers for the opportunity to present some of our recent work here. I should mention maybe my collaborators before we go ahead. So that is work done in collaboration with a number of people. We have employed a number of different techniques, which is reflected by the people. Among the younger guys, there is Alexander Witek, who was actually at the Flatiron Institute when we did this work, but more recently moved to the Max Planck in Dresden. Philip Korbos from Amsterdam, Bruce Normand from Switzerland, Friedrich Miller also from Switzerland, and Stefan Wessels group from Aachen in Germany. Okay, as was already said, it would have been nice to come in person. So I regret not being there. It looks like being a nice place, maybe another time. I'm kind of reassured that I'm not the only one who is at a distance. In particular, I'm quite happy to see two colleagues from a country that is currently at war. Okay, so where am I if I'm not there with you? Well, I'm actually in the Paris region. So our university, so this is where and who we are. So I'm allowing myself to give you a bit of perspective where I'm speaking from. So I'm speaking from France, Paris region. We are on the top left corner, which is 30 kilometers northwest of Paris. I think the big river that you can see is the Seine. Then there's a small tributary that is the Oise. The main site of our university is on the Oise, but we have sites spread all of the Paris region. Our university is a fairly recent one. It's 30 years old. And it was founded as the University of Cergy-Pontoise. It changed its name at January 1st, 2020, and we are now CY Cergy Paris University. Good. As I was saying, we are mainly on the Oise. In fact, our lab, how it's called in French, is in Pontoise, so a small town. And well, maybe not. Let's not go into further details, except saying that this is Impressionist country, and so Camille Pissarro, who is considered father of Impressionist, spent half of his career in Pontoise, and Vincent van Gogh was close by in Auvers. This is less than 10 kilometers distance from me. I guess if you don't know Camille Pissarro, I guess you might know Vincent van Gogh. Okay, and they painted here in the 19th century. Here's a picture there, that Camille Pissarro painted in Pontoise in 1877. And Vincent van Gogh did a lot of famous paintings in Auvers. This is a painting that you might know. And in fact, you can go and visit the places that have been painted and you can still recognize them today. So short, I think we have a nice location here. We also have a visitor program. So if anybody is ever interested in visiting, do think about us. But now let's move to physics. And so I'm planning to talk about strontium copper borate, which is a concrete substance, but a very interesting one, as far as I believe. That exhibits lots of interesting phenomena. There are plateaus in the magnetization curves. There are bound states in the excitation spectrum. And related to that, there's a rich phase diagram that actually is reminiscent of the phase diagram of water. And well, I'm a theorist, so for us to study that rich physics, it is important that we have numerical methods, that we have methods, in particular numerical ones, that we can use to study these properties. And most of that here, what I'm going to present today, is final temperature. And so there has been recent important progress in these numerical methods, and we're able to do things that we were not able to do a few years back. Well, I've listed some references below here, and that I'm planning to touch on. You will see that it spreads over a certain period of time, but that's related to the fact that we had some method development going on. Okay, now, since I'm the first speaker, I think I should maybe do a bit of broader introduction. And so before really going into the topic that I want to talk about, I will give you a bit of background on frustrated magnetism, and I will start with the Kagome lattice. And the kind of standard example for illustrating frustrated magnetism is the triangle. So the point is, triangle has 3 corners, and if you put an antiferromagnetic interaction on it, you can align 2 spins in antiparallel. That is possible, but if 2 spins are antiparallel, then the third one cannot satisfy both any longer, so it doesn't know where to point. Well, then if you forget about this and you put the spin somehow, that has the effect that any direction of the spin will do. And that means that basically at the molecular field level, there's an extinction of molecular fields, and you get a classical degeneracy. Of course, we know that this is not the solution for the Heisenberg bottom-line triangle, and you get a 120-degree structure, but at least for the Ising model, that would be it. Okay, and now you can carry that over to lattices by making networks of corner-sharing triangles. So Kagome lattice comes from Japanese, from the basket that is shown on the right here. But it's actually not any recent invention. It has been known to mankind for a long time, as you can see from this stone window. That is a copy of apparently something older, and this comes from already the year 715. Okay, so here, that's what we're interested in. The blue lines are the Kagome lattice, corner-sharing triangles. Let's put spins on them. And since we want to do physics and not history of art, let me remove the background pictures, such that you can see more clearly what is going on here. Now, in the middle, if you look at this, you might see a hexagon on which the 6 spins happen to be anti-parallel aligned in that particular configuration. And the point is that now you can play collectively for this hexagon the same game as you played for the triangle. And so meaning that you can collectively rotate all the spins on this hexagon, and there will be no change of energy. So the degeneracy you had on the triangle actually does carry over to the Kagome lattice, and there you really do get at the classical level the ground state degeneracy, meaning 0 temperature entropy. And the consequence of such things is that you get very rich physics. And here I'm just quoting one example. These are the magnetization curves for 0 temperature magnetization curves for a spin 1/2 model. So no, not the classical, but the extreme quantum case. So the trend is, the point is that there's a tendency in such highly frustrated magnets to have rich physics. In particular, here you see plateaus in the magnetization curve on the left panel. It's some things we did almost 10 years ago. The point is you have magnetization plateaus here at 1/3, 5/9, and 7/9 in the magnetization curve. The other steps are finite size effects, because these are small systems. The right panel shows you a similar computation by a different group that used a different method, but the conclusions are the same. They see the same 3 plateaus. And they might have seen another plateau at 1/9 of the saturation magnetization that we were unable to resolve. Okay, so the upshot is there's exciting phenomena like magnetization plateaus at rational fractions of the saturation magnetization in such highly frustrated magnets. And although I picked here 10-year-old work, there has been recent progress, so these problems have been investigated further. There's more recent work, and there are other things that you can discuss about that. But now let me go to the real topic I want to talk about. This is the Shastry-Sutherland model, which is also a frustrated magnet, which you get here by putting, so these are kind of the triangular arrangement is a bit different, so they are sharing some baselines, such that you can consider them as the square lattice with diagonal couplings on the square lattice. That was introduced in a 1981 paper, so 40 years ago, and that is a 2-page conference proceeding. And well, I checked today the number of citations in the Web of Science, and that conference proceeding has 631 citations in the Web of Science as of today. And I think it's quite remarkable to have so many citations of a conference proceeding. At least the authors definitely at the time, with Shastry, with Sutherland and Andreas, Shastry did not expect to have so much impact. Now, what is the point here? The point is if you put these if you put on the diagonal strong diamonds, you get an exact ground state, which is a product of dimer singlets. And it's an exact eigenstate of this, it's not only an exact eigenstate, in fact, for the strong dimer coupling, it's the exact ground state of this model. There, in the original paper, they also had a kind of phase diagram where the vertical axis is here the ratio of the coupling in the dimers and the square lattice couplings. The horizontal axis is the inverse of the spin value, so the extreme quantum limit spin 1/2 is on the right side. And you see that for strong quantum case and strong dimer coupling, you get this dimer product state. Otherwise, for small coupling, dimer coupling, you get a classical nil antiferromagnet. Okay, so now the point why this attracted so much attention is that there's actually a realization of that lattice in a material that is strontium copper borate. And so the magnetic ions here are copper ions, and the coppers are red. And you see that there are always pairs of coppers that form a dimer. And if you stare a while at it, you might see that the geometry is exactly the same as you have on the left-hand side in the sketch. So strontium copper borate is in fact realizing that model. And since copper 2+ is copper is in the 2+ oxidation state, so you have a spin 1/2 system. And so basically what strontium copper borate is doing, it is realizing that exact dimer product state, but it's pretty close to the transition to the nil state. So it is on the right of this plot and close to the transition. Good. So that came up actually in a 1999 paper, and already in this 1999 paper, people measured the magnetization curve, and well, in some sense, it's a low field magnetization curve here, but it's measured up to 40 Tesla, which is not small at 0.5 Kelvin, but for that compound, it's low fields, and so what you see here is that already at that time, we see a spin gap, and they did see 2 further plateaus at 1/8 and 1/4 of the saturation magnetization. On the right, there's a more recent plot for strontium copper borate, for the magnetization curve of strontium copper borate. Well, that is work that I happen to be involved in. and that is a measurement of magnetization measurement going up to roughly 110 Tesla. And you have less resolution at low fields here, but you do see two very pronounced plateaus at 1/3 and 1/2 of the saturation magnetization. It's still not the full story. There are other plateaus that have been observed in other experiments. So the point is that strontium copper borate might be the compound around that has the richest magnetization curve that has been studied so far. Okay, so that is magnetization curve. There has been a lot of effort related to strontium copper borate because of that. And something that was done is neutron scattering. So on the left, I'm showing you again the structure. Maybe this orthogonal dimer arrangement is clearer here in that type of representation of strontium copper borate. And on the right, you see neutron scattering from 2004. And what you see first of all is that you have here at lower temperatures, you have a almost flat band in the single particle channel. And that is again another manifestation of geometric frustration. That you have absence of propagation, that you have no kinetic energy, that excitations are localized is again an effect of strong geometric frustration. Okay. Now you might ask yourself questions like, well, if the dynamics is absent at 0 temperature, does actually temperature generate dynamics? In fact, already at that time, people did look at temperature dependence, and if they're going from 1.4 Kelvin to 21 Kelvin, the dynamic response actually changed a lot. I should also mention that there was a study at roughly the same time, so a theoretical study by Janos Bonka and collaborator, who did numerical investigation of a quite small system. And well, since the system is very small, I'm not going to comment further on that particular investigation. Okay, now here's another version of the same thing, and that is actually the experiment that motivated the work that I'm going to talk about, that I'm going to present in the rest of this talk. So this is 2014. It's a few years old, but things are going a bit slowly on in that field. So again, you see here in the upper left panel, you see a flat dispersion relation at 2 Kelvin. So, and again, this fingerprint of strong geometric frustration, and the energy 3 milli-electron volt corresponds to the excitation energy of 35 Kelvin. Now, what is really striking in the rest of these plots is that if you go to a temperature of 15 Kelvin, which should be significantly below the 35 Kelvin, that the dynamic response is completely changed. You see this in the scans, you see this in the intensity integrated things here. Basically, the energy scale where things here are changing, temperature scale where things are changing is 10 Kelvin, which is a factor 3 below what should be the intrinsic energy scale according to neutrons. And this is really extremely unusual and needs to be understood. And so that is basically a core for understanding thermodynamics. Okay. Before we really get going, I have another postscriptum to make. That is on the ground state phase diagram for the spin 1/2 case. So if you remember, let's go back here to the old Shastry-Sutherland work. There were two phases. Particularly here was a direct phase transition for spin 1/2 between the Néel and the quantum spin liquid state. Now, more recent work actually showing that here, so the strong dimer limit is on the left. This is the exact dimer ground state. If you have strong square lattice coupling, while on the other hand, you get a male antiferromagnet. That is the old ones. What was overlooked by Shastry and Sutherland is that there's a small intermediate phase where you have a plaquette phase where you have singlets formed on the intermediate on the voids, on the square lattice voids. So that doesn't change the fundamentals, but it will be relevant for further discussion that there's actually an intermediate phase. And people were actually fighting for a decade or so about the existence of the intermediate phase. But I think in the meantime, that is quite well established that it exists. Okay, now I forgot to insist that Strontium copper is in the exact dimer state phase, but very close to the phase transition. And so if it is close to the phase transition, you might actually hope that you might drive it across the phase transition by applying, for example, pressure. And people have tried to do this. And here are some previous works. So here is an attempt. The upper left is an attempt to drive it from the exact dimer state to the nil state by applying pressure. These also set a plaquette phase in between that unfortunately didn't correspond to expectations. There's another work that is now came out 2 years ago, that they measured the spin gap here as a function of pressure. And both of these works, I think, claim to have seen a phase transition. But once again, in a pressure cell, you can't do that much. So again, this is mostly thermodynamic measurement, and that means another argument to understand the thermodynamics. Okay, now after this long introduction, let me tell you what I want to use the. Right. By the way, when I'm actually supposed to stop. So how much time am I supposed to leave for discussion? I seem to have lost the chairman. Well, anyway, if there's anything that doesn't come across, I can't point. And so if there's anything that doesn't get across, please interrupt me. And if you have questions, and to this point might be a good point. Okay, good. So then let's move on. So I presented my motivation, and now what I really want to do is to tell you how we tackled the thermodynamics, and we approached it with 3 methods, and namely quantum Monte Carlo, exact generalization, and infinite, so-called infinite projected rectangle pair states. So some of these are new developments, and it is always good to have different methods as cross-checks to know what you're doing. So I'm using that as an example to show you what you can do in the meantime. Physics-wise, there I will want to go back to the low energy bound states and comment quickly on how we believe that they're linked to the thermodynamics. And then I will also want to come back to the pressure experiments. So I'll show you yet another experiment and try to explain a bit how this fits in with the context of water. And then I will, of course, conclude. Okay, now let's start with the methods. And so what is the issue? So of course, when this compound came out in 1999 or so, people of course immediately tried to explain the experiment that is shown here in red. And one thing that they tried to do is to do series expansions, either high temperature series or dimer series. And well, you can fit the high temperature tail of the susceptibility here in these graphs nicely. But the point is, whatever you do, this breaks down in the low temperature region. So you really don't know what is happening in the low temperature region based on the thermodynamics. And that is actually the region of interest for us. So that was useful because, you know, I told you where this where strontium copper void is located in the phase diagram. That location comes from such an analysis, but unfortunately you don't get to the low temperature regime by that method. So people try to do something else. In the early days, they tried to do exact normalization. And here, again, red is experimental data and black is the theory from that time. Left is magnetic susceptibility, right is specific heat. They were claiming that the fit here for a coupling ratio of 0.635 should do the job. But now if you compare at least these data sets, well, I'm not that sure about the comparison. And then if you think about it, that was done for 16 or 20 spins in 2 dimensions. 16 in 2 dimensions is 4 by 4. It's really a small system. And in fact, for the 16-side system, it's not only 4 by 4, it's also 2 to the 4. So the 16-side system doesn't really know whether it's 2 dimensions or 4 dimensions. So you might have reservations about the trustworthiness of these results. And so therefore, at least I wasn't happy with that particular computation. So the first thing that we did is actually doing quantum Monte Carlo. And I personally like very much a version of quantum Monte Carlo that runs under the heading of stochastic series expansion. And that was developed by Anders Sandvik since the early 1990s. And I'm relying here on the expertise of Stefan Wessel. So the idea is pretty simple and quite general. What you do is you split your Hamiltonian into bond parts. And the bond terms are then split into a diagonal and off-diagonal terms. With that splitting, then you use the high temperature expansion of the partition function, meaning you insert the power series representation for the exponential. And then for the traces here of the powers of the minus the Hamiltonian, you use matrix elements in a given basis. So you choose a basis, and then you basically end up with a huge sum of terms of products. That might look nasty, but the thing is Monte Carlo is meant exactly for evaluating such huge sums. And you just use here these products of matrix elements as your weights. The problem is there's a minus sign here, and well, then it depends on your Hamiltonian whether it actually gets negative. But what are supposed to be probabilities might actually be negative. And that is the so-called sign problem. And well, for the diagonal parts, you don't have a problem because you can add a constant and make them positive. The troublemakers are the off-diagonal terms. And let me give you an example and go back to a single triangle where I'm assuming here an initial configuration of 2 spins up at the bottom and a spin down at the top. And the off-diagonal operator here is the pair flip of 2 spins across a bond. And you see that you can flip here spins along one edge, you flip them along a second edge, you flip them along a third edge, and you're back to the initial configuration. Meaning that there is a diagonal matrix element that contains 3 products of minus this thing here, and that is definitely negative. So if you have a triangle in your system, these off-diagonal terms give you negative weights if you use that basis here. Well, the standard way out is to close your eyes and take the absolute value of these matrix elements and sample with respect to the absolute values. Then, so you sample with respect to the absolute values, but then in the measurements you have to restore the sign. You can run the code in that way, but the problem is that the average sign can get exponentially small, and it usually does get exponentially small if you have a sign problem. And if you try to estimate error bars for an exponentially small quantity, they are relatively exponentially large. And that means you get exponentially large error bars. But, and now this is the good news, this finding is basis dependent. So you might have a chance to do better by changing to different bases. And for the Shastry-Sutherland model, the basis of choice is the dimer basis. So you pass to eigenstates of a spin 1/2 dimer. So the singlet and the 3 triplet components. And well, there's some freedom here, but we choose to work with a well-defined magnetization. In some sense, you can cast it in a different language in terms of rewriting the Hamiltonian in terms of the total spin operator of a dimer and the spin difference operator of a dimer. But if you then generalize the orthogonal dimer arrangement by introducing another coupling J2 here, then you can write the dimer-dimer coupling that is sketched here in terms of the total spin times total spin coupling, and the correction term that is coupling the total to the difference. Well, so the first line would be fine. There's no negative sign in the first line. The second line might give you negative sign, as you might see from the matrix elements here of the D operator in that dimer basis. So there are minus signs or plus signs, so they're different signs. So there might be a sign problem with these signs. But instead of thinking very long about it, it's better to try it out. Okay, and here's a graph of the average sign. So this is 10 by 10 dimers on the left, which is 100 spins at a rather low temperature. And you see that the sign stays quite close. So green means it's close to 1. It's not exponentially small, it's close to 1 in most of the dimer phase. So the vertical axis is additional coupling J2. The horizontal phase is the coupling between dimers over the dimer coupling. The sign then does get small once you go into the nil phase, but that was kind of the idea. The basis was adapted to the dimer phase, and therefore we were hoping to be able to work in the dimer phase. On the right-hand side, you see a graph here of the sign, average sign as a function of temperature, and that is for different ratios. And the point is the average sign is not 1, so there is a sign problem. There's a drop as when you come from high temperature that is more severe if you go to a stronger coupling between the dimers. But if the coupling is not too strong, the sign recovers at low temperature. For example, if you see the black curve, the sign is not strictly 1, but it's good enough to work with, definitely. And so the only thing is that if you crank up the interdimer coupling too much, the sign doesn't recover at low temperatures any longer. Now, here is another perspective on the same kind of thing by focusing here on the case of a ratio 0.5 of the couplings, the Shastry-Sutherland model, and on the right 0.55. In both cases here, you have open symbols that show you the single spin basis, so the one that I discussed before, and the full symbols show you the dimer basis, the average sign. And you see that for a given system size, the dimer basis is always better than the single spin basis. In the single spin basis, you actually do see always that the average sign goes exponentially to 0 as you go to low temperatures, and that gets worse if you go to bigger systems. So here is, if you go from 36 to 64 spins, you actually basically can't do anything below a temperature below 0.5. So at the ratio of 0.5 in the left case, this is cured by the dimer basis for effectively up to 200 spins. On the right-hand side, the dimer basis doesn't cure that completely. It also goes to 0. So it also goes to 0. But even the 200 spin system here, the sign is still significantly better than low temperature than the smaller systems in the single site basis. Okay, before I actually show you results obtained with that, let's ask what is going on here. So we were actually a bit disappointed. So the left is good, but the right we didn't like. And what is going on here? Well, the thing is, if you change, if you take the absolute value of the sign, you actually change the model. And that model has a phase transition. So this, what we call the sign-free model, that has a phase transition at an exchange ratio that is smaller than the phase transition in the Shastry and in the real Shastry-Sutherland model. So you still you also have at weak interdimer coupling, you have the same exact dimer ground state, which is good, and that is the reason why it works. But then there is a phase transition in this sign-free model that precedes the phase transition in the true model. So if you wish, there's an algorithmic phase transition, and so you can work until you get there. After that, it becomes again more difficult. Good. Here, I'm showing you some results that are obtained with the method. On the left-hand side, you see the specific heat. On the right-hand side, you see the magnetic susceptibility. And that is being done now. These are quantum Monte Carlo results for an effective system of 200 spins. And the first message is that you get very clean data up to a ratio of 0.5. So quantum Monte Carlo works, you get nice results on big system sizes. And from the physics point of view, you see that there's a nose here emerging in the specific heat corresponding to the edge here in the susceptibility on the right-hand side, meaning that you get the emergence of a low energy scale in the thermodynamics if you crank up the interdimer coupling. Now, if you go a bit further, well, actually, let's have a look at the data set ratio of 0.5 here. So I'm basically showing you these data again, but giving you more for comparison. I'm giving you ED, mainly in particular for 20 sites, the old historical one. Then you see quantum Monte Carlo in a single spin basis for 36 and 64 sites, and dimer by quantum Monte Carlo in the dimer basis. And yeah, so what can you see here? So the quantum Monte Carlo in a dimer basis works and gives you clean results, and you can compare system size and be sure that 200 is big enough. If you are in a spin basis, you get an exponential blow up of the errors bars as you come from whole temperatures as anticipated. So you do see that here. And well, maybe you can barely get to the maximum of the susceptibility, but that's it. You don't get in the low temperature into the low temperature region. So the spin basis quantum Monte Carlo is basically useless. The old exact dimerization for 20 sites here is not doing so badly for this ratio, except that you can actually see some deviation at the immediate temperature in the specific heat here. So if you look very closely at the location pointed to by the arrow, you do see a deviation there. But as soon as you go to 36 spins, you don't see any final size effects any longer. Right. Now, if you crank this up a bit further, it stops looking as nice. So now the dimer basis quantum Monte Carlo doesn't get to the low temperatures any longer either. So this is now the ratio 0.55. And yeah, but first of all, the single spin basis quantum Monte Carlo breaks down long before you get there. With the dimer basis, you can approximately still resolve the maxima of the thermodynamics. But with respect to the market rate data for this larger ratio, now you can also see that the differences with respect to ED, in particular in the specific heat, they get bigger as you crank up this exchange phase. Well, that is about the limit that we can go with quantum Monte Carlo. Strontium copper borate is a bit further, so unfortunately, by that method, we can't get to strontium copper borate. So we have tried two other methods. One is exactly. And since I see time running, so maybe I will show go a bit quickly on that. So that is work done by Alexander Vitek. Basically, what we have been doing here is so to go further than the all 20 sites, use the idea that is so-called thermal pure quantum states, which is related to the finite temperature Lanczos method. The very rough idea is that you basically estimate a trace by a random average. Trace of any observable can be estimated by a random average, and the point is that you can, if the Hilbert space dimension is large, you can get away with very small, with very few random states for a large Hilbert space dimension. That is at infinite temperature. Then going to finite temperature, you do an imaginary time evolution, and what we do is we use it by the Lanczos method. So with that, you can do then imagery. You can then do thermodynamics for a bigger system, and here I'm showing you now results here up to 40 sites at the ratio relevant to strontium copper borate. This is going up to 40 spins with typically 5 vectors for 40 spins. And you can see that you can get 4 to 40 spins. What is a bit funny is that you get error bars on exactly data. This is because of the sampling. You do see now finite size effects, but you can also see that from the insets, at least here, you can see that mainly 40 spins for that particular ratio is good enough. So you need to go to 40, but that should do the job. 20, on the other hand, in the case of the specificity, is not enough. From the point of view of physics, you do get a sharper, so this maximum of the specific heat and the edge here in the magnetic susceptibility do get sharper. So you actually do have a more pronounced low energy scale here than you had at weaker couplings. Okay. Now, after having done that, we had another collaborator telling us I can also do it. And so that is Philip Corbos, who was using IPEPs. That is a tensor network that works in the thermodynamic limit at finite temperature. Well, I think I will skip over the details. So Philip is really an expert on that. The point is that you optimize the degrees of freedom to represent your system correctly. And here I'm showing you again that chi is relevant to strontium copper borate. And now I'm comparing here in red is, well, maybe you should take the magenta dashed line that is IPEPs for the lowest degree of approximation, so with the lowest artifacts. You can see that if you, so there's this internal bond dimension parameter that you need to crank up to make it more accurate. And then if you compare this with thermal pure quantum states, you see that basically the IPEPs and the thermal pure quantum states are indistinguishable. At high temperatures on a small system, you can still do quantum Monte Carlo. You don't get to low temperatures. But basically all methods that we have here are consistent. Therefore, we're confident that whatever we do, I mean, either IPEPs or thermal pure quantum states, they're actually reliable. I spent a lot of time talking about quantum Monte Carlo. I do like the quantum Monte Carlo, but I have to confess that for that particular problem here, IPEPs seems to be the best method in the sense that you rather cheaply get the best, you get good accuracy without the lowest cost of the three methods. Okay, now I'm going back here to the old experimental data, and here's the old experiments. So the circles are the old experiments. The orange curve here corresponds to what was the old exactization data. And the ratio is basically the ratio that was determined before. We have readjusted the overall scale. And what you see is that with the new methods, we get basically a perfect fit of the specific heat here without any further adjustable parameters. But at high temperatures, there's a bit of an issue that you have phonons that you have to get rid of. So the deviation at high temperatures, I believe, comes from phonons. But you see here, there was a bit of deviation in the old data, so the 20-side system was not big enough. If you go to bigger systems or the thermodynamic limit. Yeah. So bigger systems, meaning here 36 or 40 for that particular case, it seems to be sufficient. You get rid of this discrepancy and you get a perfect fit. I should maybe insist here that if you look at this, so people might have known this, the characteristic energy scale in C here is 10 Kelvin. So the maximum is at the order of 10 Kelvin, which is not the scale that you got from neutrons, which is 35 Kelvin. It's a much lower energy scale. Now, the question is, where does this low energy scale come from? And so let me very quickly comment on where this low energy scale comes from. If you look at the excitation spectrum, there's a single triplet excitation that is basically that you can trace from the isolated dimer from the left to the phase transition. Now you can form two particle scattering states from the single particle, and so you get the two particle scattering continuum that is here sketched in light blue. Now the point is, if you look at the spectrum, there's actually a bound state formation. So you get actually a singlet bound state that have lower energy than the two particle scattering threshold. And these singlets come down as you increase the coupling. And if you go to the transition to the phase, plaquette phase that is at the right, they do cross below the single particle excitation. So the point is you get low energy singlets that have an energy below the even below the single particle threshold, and these are singlets. Okay, here is a bit of more details on the number of bound states that you get below the two particle scattering states. So here left is one system size, and you see that the number of bound states are actually starting to even exceed the number of scattering states as you go very close to the phase transition. And here is for the parameter ratio on the right, relevant to strength and copper void as a function of system size. You see that if you go to bigger systems, you get more singlet bound state than you have. You also get triplet bound states, but you get more. So the number of bound states below the two particle scattering threshold goes with system size. And so upon approaching the phase transition and going to bigger systems, you get more and more bound states, and in particular, you get singlet bound states. And we believe that these singlet bounds that are not being seen by neutrons, so neutrons are blind to the single particle bound states, are the reason behind the unusual thermodynamics. Okay, so for the last 5 minutes or so, I want to quickly walk you through a recent experiment that was then done after we had kind of developed the methods. So here on the top left is an experimental result for the specific heat of strontium and copper borate, low temperatures under pressure. What you see here is a maximum as a function of pressure that is actually developing in a peak here, and a strong peak at a particular pressure. And by other methods, you can actually trace that to a transition, first order transition between the dimer singlet and the plaquette state at 0 temperature. So that is connected to so that red spot here is connected to by first order line of first order transitions to the 0 temperature phases. Well, now that we have developed the methods, we can do the computation as a function of exchange ratio here of the specific heat. This is IPEX, and you can see exactly the same features. And you can actually also then use that to draw the phase diagram in the external field. And you have this dimer phase that is stable in an external field. The plaquette phase also survives a bit of an external field. And then between them, there's a surface of transitions in first order transitions. And this surface of first order transition then actually terminates at this temperature of roughly 4 Kelvin at a critical point. Good. And that whole picture, and that was the main teaser of the paper, it actually does look very reminiscent of water. So here's the phase diagram of water, specific heat of water as a function of pressure on the horizontal axis and temperature on the vertical axis. You do also get a critical endpoint. So at a high pressure, below that pressure, you can distinguish water from vapor. Above, you can't. And they are separated by a first order line. So the structure of the phase diagram is exactly the same as you have with water. Well, you might argue that it doesn't look exactly the same. And so that is kind of probably the last point I want to make. So going back to the left, in fact, you can argue that what is happening in here is also in water, is in fact Ising physics. And so in fact, so this is a 2D model, a quantum model, where we have our quantum system, 2D quantum system that we have studied at fine temperature. You can compare this to the classical square lattice Ising model in the magnetic field. And if you compute the specific heat like of that, then you see more or less the same structures, like as you see here in Strontium copper borate, except that the energy scale is quite different. And so after we published that work here, we had a young guy, Lukas Weber, who came up with an idea to relate this to what is going on in water. Well, so the Ising model looks a bit like Strontium copper borate, but doesn't look like water. Now, what Lukas came up is the idea to say, well, wait a minute, how should I know the temperature axis is temperature axis, magnetic field corresponds to pressure? I might actually have a rotation of these parameters. And so if you change parameters on temperature and field, then you actually mix observables. And doing this mixing here, you do an increasing rotation. And so you see actually the specific heat here plot changing as a function of rotation angle. So the upper left plot is exactly this Ising, square lattice Ising model. But if you have rotated this here to the bottom right, then it actually does look exactly like what you get in water. So what we really do believe is that these two kind of physics is really the same physics. So if you wish, this phase diagram of water is 200 years old, and now you have actually in a quantum system exactly the same phase diagram, except at lower temperatures and very different parameter regime. And the difference here is essentially how the parameters, so how mainly pressure is related to an effective field. Okay, good. So with that, I think I should leave a bit of time for discussion. And so let me again tell you what was the main point of telling you. I hope I got across that Strontium copper borate is a very interesting system. I've shown you the magnetization curves. I've talked about thermodynamics, and I tried to explain you how the unusual thermodynamics is related to unusual bound states in the excitation spectrum. And if you put a bit of pressure on it, you get a phase diagram that looks very much like water. What we haven't done yet is we haven't done the finite temperature neutron scattering yet. We are almost there, but it's on the to-do list. And from the technical point of view, the message is that recent progress in numerical methods actually now allows us a detailed finite temperature study of at least some highly frustrated magnets that at least a few years ago was out of reach. Well, again, a few references. I should mention that although I have focused on a particular application, on a particular model here, at least the quantum Monte Carlo and also the other progress is useful in other models. And I suspect that Joseph might mention another application of the quantum Monte Carlo in his talk in 3 days. And although I have been in France for quite some while, that work has benefited from financial support from the German Science Foundation. So I need to thank them and for the financial support. And I would like to thank you for your attention. Thank you very much.
Thank you, Andreas, for the nice talk. So, if you have any questions, please raise your hand online or here also at the auditorium. We'll wait a few seconds. Yeah. Joseph, please come closer.
Thank you very much, Andreas, for a very nice talk. I have a question concerning quantum Monte Carlo simulation, what you mentioned, like longest part of your talk. And you have shown that in the linear basis, you are able to resolve the sign problem, but this resolving work just up to lower interaction ratio than the one that is relevant for strontium copper borate. And my question is, if you would apply field, how does it would compare? You will be able to improve this range of interaction ratio, or there will be almost no change. But my idea is whether you will be able to explain thermodynamics around the plateaus and whether some phase transition could be studied there.
Okay, thank you, Joseph. So first comment is, I have a bit of an echo. So the first comment is that if you introduce the J2 and you make the J2 equal here to the J, you get rid of the sign problem. And that is a different model that we actually also looked at. So you can get rid of the sign problem. If you don't go there, you have to try it out, and that is an experience. So what I didn't insist on is that this actually works also in an external magnetic field. So you can easily add the external magnetic field term. The same idea works. The thing is, we haven't done it. I mean, we have only used it zero field. So it has been done for other models. For that specific model, I think nobody has done it so far. So it is an interesting question, but since nobody has done it, I don't have the answer. So it might actually work, it may not work. I don't know.
Any further question?
I have one. So,
Go on, please.
hello, Professor Andreas. Thank you for your nice talk. I have a question about the Shastry-Sutherland model. There is a variant of this model that can host a spin liquid phase in 2 dimensions in finite temperature. Thank you.
So let's maybe stay on this transparency. Well, again, have an echo.
Sorry, you can hear me? You can understand me?
Yeah, but I have an echo if I speak. So let's stick on this transparency. So the point is, on the left, we have actually superimposed the phase jet on the zero temperature phase. On the left, you have a dimer phase. That small triangle is the plaquette phase, and then you have the near stay phase. You can fight about what you call a spin liquid. But if you call this non-classically ordered states of a spin liquid, you have the dimer and the plaquette phase that are spin liquids. And now the point is, if you go to finite temperature, that first order transition line persists to a certain temperature. So that means you still kind of can identify the dimer nature of that ground state at finite temperature. There is no finite temperature phase transition into the dimer state that is forbidden by the Merman-Wagner theorem. But in some sense, that is kind of the point of the phase diagrams that I showed you later. So here you can actually see the temperatures in terms of J is not that big. It is 0.05 or so. That dimer phase has a phase. So this is not a phase transition, this maximum here, it's a crossover. But it's well defined as the finite temperature. I'm not sure if that answers your question, but that is, in my understanding, it's as close as you can get to an answer.
Okay, thank you.
So if not, we are going to thank again Professor Andreas.
Thank you.
Thank you for the nice talk, and you have a short break before the next talk. So we will return at 10:30 local time.